Assalamualaikum. Assalamualaikum. Hello, Group 18. Hello, Usama. Usama Mamun. Usama Mamun. Okay, group 9. Group 9. Hello.
Good afternoon, doctor.
Yeah.
My teammate is now entering the Zoom. So currently there is Nigel and uh,
Okay, group 9.
another member. Yeah.
Ready? Who is ready? Group 9 ready?
No, yeah, doctor. Because two are still joining in. Yeah.
Group 8. Group 8 not ready. Group 7.
Yes. Group 7 still waiting for group member.
Okay.
I already called them.
Once your group ready, you tell me in the Zoom, so we wait.
Okay. Sure. Thank you.
Good evening, Prof. Group 6 already full member. So can we start first?
Wait. Okay. Group 6.
Prof, I share the screen.
Okay.
Eh, okay. Okay. Prof, can you see my screen now?
All right. Group 6, eh?
Yeah, group 6.
Okay. Continue.
Okay.
Start.
Okay. So good evening, Prof. We are group 6. So this is our group assignment presentation. So the member of group 6 are me, Brian Sojourn, and Kam Kawai and Yak Sing Wei, 3 person. And the question assigned to us is the question set 6. So the first question is we have a unity feedback system with the transfer function given as shown here. And then the question want us to determine the appropriate value of 0, which is the Z, for overshoot to from 46 to 32. So when overshoot is 46%, our Z is 1. So when we change the overshoot to 32%, what is the Z? The question wants us to find. And this is the flow chart of how we solve the question. So first we will declare the transfer function in the MATLAB. So basically we type the transfer function in the MATLAB first, and then we fix the post value to 3.6, like this one, the P here. And then after that, we obtain the closed loop transfer function, and then we calculate the percentage overshoot. Then we display the percentage overshoot we obtain first, and then we do the comparison to see if the percentage overshoot is larger than 32 or not. If it's larger than 32, so we do a subtraction on the 0, which is the Z, by 0.01. And then we do the closed loop transfer function again. And this all step is a loop. So if somehow we obtain the percentage overshoot is not larger than 32, then it will break out from the loop, and then the Z at the moment is the Z final, which is the final answer. And then we will display the Z for overshoot 32%. And then we plot the step response of closed loop transfer function. And then we end the program. So this is our MATLAB code. So at first, from line 3 to 7 is we do like initialization. We type the transfer function, and we type the things we need, the values we need to do. For example, the S we declare first as transfer function, and then the initial Z is 1, the post is 3.6, and then the target percentage overshoot is 32. And then for the T, we set from 0 to 10 with the increment of 0.01. This is used later in the transfer function. So in line 11 is the loop lah. And then 12 to 14 is the transfer function. How we type the closed loop transfer function. So it's like this. Until line 16 is the closed loop transfer function. And then after that in line 18 is we do the step response for the closed loop transfer function. And then we obtain the max Y, the maximum value at the Y, which is the magnitude, the maximum magnitude in the step response.
Okay, proceed.
And proceed to the next question, or
Next slide.
next slide. Okay. So this is the output of our MATLAB code lah. So the left hand side is every time we obtain the overshoot, we display it here, and yeah, basically you can see it's decreasing when the Z is decreased. So until 31. So it's already lesser than the 32%. So the Z at the moment is 0.57. And the right hand side is the step response plot. So we can see that the peak amplitude is 1.32, and the steady state is extremely close to 1. But here it show overshoot is NaN because the somehow the steady state will reach to infinity. So it cannot really calculate it up. But from looking at here, we can already see is 32% from 1 to 1.32. And next, I will pass the presentation to Kam Kawai.
Okay, so this is
Hi,
our
are you
second
scared?
question.
Speed up.
Okay. So this is our second question. So this is a transfer function given for us, and it requires us to plot the frequency response of the circuit, which is the proper of the transfer function. And then this is the flowchart of our question. So first we will declare the transfer function in the MATLAB with the specification given, and then we will use the block function to plot the transfer function with the grid. And then this is our MATLAB code for this question. The R1, R2, C1, C2 is the value that we given, and then the G is our transfer function, which is the V out minus V in, and then we use the block G and grid to get the frequency response of the transfer function, which is like this one. This is the plot diagram of our transfer function. It has the magnitude and the phase. And then next question is this one. This is question given. The time delay given is 0.2 second delay, and then we are required to plot the phase margin for the gain from 0.1 until 10, and then we have to determine the gain that will get the maximum phase margin. And then this is our flowchart for this question. So first we will initialize the time delay just now is the 0.2, and then the range of k, and then we will declare the transfer function with the specification given, and then now we will try to check the whether the I is smaller than the length of the transfer function, and then if it's true, then it will calculate the phase margin from now, and then it will increase the 1. And then if the I is larger than the length of the function, then it will plot the graph of the phase margin versus the gain, and then we will obtain the maximum phase margin and gain value at the maximum phase margin, and then we will display the maximum phase margin degree and the gain value. So now this is our MATLAB code. So first the code we will initialize the specification given, and then the number 8 and 9 is the transfer function, and it will be times together to get our transfer function in the line 11, and then for line 13 until 15 is a loop, so it will keep obtaining the phase margin value, and then after we done, then it will plot the phase margin versus gain graph of the phase margin versus gain. And then from there we will get the maximum phase margin by using the code as shown at the 25 until 28. And then this is our output of the MATLAB code. So this is the curve of, so this is a graph being plotted from the code. So from there we can see that the x-axis is the gain, and y-axis is 67.2533 degree, and then the K when the phase margin is reached is 2.42.
Next, I will
And
explain
then
about the question 9.1. Question 9.1 is that we need to verify for this open loop transfer function, then the gain margin is infinity and the phase margin is 9.8. So this is our flowchart for solving this question. First, we declare the transfer function in the MATLAB, then we plot the proper with the grid. Then we obtain the gain margin and the phase margin for the transfer function and display the gain margin and the phase margin. So this is a MATLAB code we wrote for display this question. First, we declare the transfer function in line 3 and 4. Then we plot the proper and enable the grid on, and 8 and 9. Then we get a gain margin and phase margin. Then we display in the string. So this is the result for this method code. And as you can see that this is the phase margin is 9.79, which is close to that. And the gain margin is infinite. And the right side is the block plot. Which also verify that the phase margin is 9.8 when the gain margin is infinite. The next question is, given an open loop transfer function, then we need to find the k when the t is 0.2. And the k is when the phase margin is more or equal to 45 degrees. So for question A, the flow chart will be like this. We initialize the time and the value k. Then we declare the transfer function. Then we obtain the phase margin and compare to the phase margin with the 45 degree. If not, then it will continue looping. And when we get the target k we want, then it will display the k for the phase margin more than equal to 45 degree. So this is the method code for the question 9.4a. For line to 3 to 6 is declare the transfer function. Then 8 to 14 is the loop for finding the target k we want. Then 16 is display the k value.
Jinwei.
Yes.
Previous slide. Previous slide.
Hello?
Previous.
Hello?
Previous.
Hello? Okay.
Not this one. Previous. Forward. Forward.
Forward.
Forward. Forward. What is this? Jinwei, tilde.
The first one is for this syntax is gain margin and phase margin. But we don't need the gain margin, so I just put it there, which is we ignore the gain margin. We don't need to obtain that value.
Oh. Okay.
Yeah.
Proceed.
Okay. Okay. Next. So after running the code, the k value for gain margin and for phase margin more than equal to 45 degrees is around 10.01 to 13.01. So there's question B for 9.6. Back to the question. So for question B, we need to plot the phase margin versus t, which is the time for the k we found in the part A, which is just now. And with the t range is 0 until 0.3 seconds. For the flow chart, for solving this question, we use this flow chart, which is we initialize the new time delay and also the k value. Then we declare the transfer function. Then also we use the looping to find the phase margin. Then we plot the graph of phase margin versus t, which is the time. This is the method code, and the 19 and until 21 is declaring the transfer function, and 22 until 25 line is finding the phase margin. Then 29 to 33 line is to plot the graph. So this is the result graph we obtained from the code just now. And yeah.
Jinwei, Brian So.
Yes, Prof.
What is the equation for this line?
Equation for this line. The equation is
No.
the equation.
Don't change the slide.
The equation is same as the question given transfer function. Just we fix the k value to 0.0.
No. The equation of this line, the blue line.
The equation of blue line.
Kam kawan.
Y equal mx. Okay.
Kam kawan.
Yeah. It is what of blue line.
Jinwei, what is the equation of the blue line? Jinwei?
Yes. If using y equal mx plus c, then the c will be 140. Then the slope will be what? Wait, I calculate. The c is 140, then the slope is around
What is T?
46 something.
What is T?
What?
What is
T
T?
is a x.
I know this one. What is the unit?
Oh, second time.
T itu apa? Period ke? What is T?
Second.
Time.
Time in second.
Time. Time. It should be like this. This one is period.
Oh,
Time.
okay.
Yeah. Oh. The slope.
Sorry.
The slope. The slope.
The slope I find is like 466 something. 466.67 maybe.
Minus 466. Liu.
Yeah.
Liu.
Yeah, Liu.
Plus 140. This is
40.
the equation.
Yeah.
So you must include this in the report. It's analysis.
Oh, okay. No problem.
Okay. Continue.
Okay. And next. So based on the the assignment we do, we can know that we can observe that when the percent overshoot is decreased, the pole and the value of pole and the transfer function is fixed. The zero value will be increased, like the question 10.8. Then for the time delay increase, the phase margin will decrease, like the question 9.4b just now.
Okay.
Next.
Finish. Okay, finish.
Finish it.
Right. Okay. Thank you very much. Group number.
Thank you, Doctor.
Okay, thank you, Doctor.
Six.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Prof. lah.
Okay, group number 7. Group number 7. Group number 6, quit
Yeah. Group 7 here.
on video.
Oh, okay.
Jinwei, quit. Kawai, quit.
Okay.
All right, thank you,
So,
Prof.
quit.
Thank you, Prof.
Hold on.
Okay.
Let me jot down the name.
So our is group 7. Mark Go, Chunwen, Alexander Wong, Heng Yi, and Ong Xue. Our question is number 1.
Wait.
So this is
Wait.
okay.
Slide. Okay.
Okay, proceed.
Continue.
Okay, so this is the flow.
Where is the question?
Question is here. Oh, sorry. Just now put wrong arrangement.
Oh my god. Okay.
Okay, but the send
Fast one.
here is the question. 7.1 until 7.10.
Right. Fast one.
Okay. Okay, first one. Okay. So this is the flowchart for the question 7.1 until 7.4. We use the similar flowchart, while the 7.10 have a different flowchart. Okay, so this is the question for 7.1 manual calculation, and this is the graph for from the manual calculation, and this is for 7.1C, and this is for 7.2. And this is
Continue.
This is the manual calculation for 7.1B and also 7.1B. And this is calculation for 7.4 lah, 7.4. Okay.
This is the manual calculation for 7.10.
Yeah, so this is our MATLAB result refer for the 7.1a. Yeah, we also sign out the some important points. For example, the poles and zeros. And this is for the 7.1c, and this is for 7.2. All the important points already point out.
Can go to 7.1B. Okay. The group focus is the shape like this, and all the poles and the okay. And this is okay. Next. This is the focus for 7.1B. This is definitely the same what manual calculation. For manual calculation, the graph is almost the same like this. Okay, and this is next. Next figure. And this is the graph, okay, for 7.4. So what I calculate is I found out that I use the average table to find the range of the t. So the range of t is from 0 to 10. So this is the graph when t is 5 together. Okay, next. This is a graph of when t equals to 25. The graph is a shape like this. Okay.
Okay, for 7.0, we need to calculate the range for the k value for which the system is stable. So I take the minimum k value and the maximum k value. This is minimum k value, k equal to 0. Next one. And this is the maximum k value, k equal to 41.15.
This way.
Yeah, so this is for the simulation for 7.1a. The step response according to the transfer function, 7.1c, and also 7.2.
Can go to mine. This is the 7.1B, the step response for clearing the transfer function. Okay, so can go to 7.1B. Okay. Right.
And this is the step response for 7.10 at minimum k. And this is for maximum k.
Yeah, so this is the observations, ideas, suggestions, findings, and also the improvements for this project. So basically, it's about the poles and zeros, break in, break away points, and also the asymptotes of the system. Besides that, the gain between the relationship between gain and stability of the system is also very important for this topic. Yeah, that's all. Thank you.
No Excel. Excel and Simulink not included.
Simulink, yes, but for the Excel, we just send with the file. We not showing in the power slide.
Not showing the slide, but
yeah, we already do it and attach with the PowerPoint.
okay.
Already sent you.
Okay. I will check the attachment.
Okay, thank
Thank you
you.
very much, Group 7.
Thank you.
Thank you, Paul.
Thank you, Doctor.
Group number 8.
Bye-bye, Doctor. Thank you, Doctor.
Share your slide.
Okay, yeah, better. Wait.
Group number 7.
Yeah, wait, Doctor. Saya screen. This one.
On video. Group number 8 on video. Group number 8 on video.
Okay.
On video. Group 8.
Oh, video. All right.
Proceed.
Okay. Misalkan full screen. Okay. Assalamualaikum and good evening, Doctor. We are from Group 8. Next slide. Okay. My group member is Muhammad Hafiz Izzuddin, Muhammad Ashraf, and me, Muhammad Aidil Hakimi. And we got question number 2. Okay, so the first question, question 7.5. We are given GS S plus 2 over S square, and we need to find the gain K with damping ratio 0.707. Okay, so we plot the transfer function into the MATLAB, and we will get this shape. Next. By using our mouse, we find the closed loop dominant pole with damping ratio 0.707, and we got S equal to -2 plus J2. And after we got the dominant closed loop pole, we substitute the equation, the dominant pole into this equation, K equal to S squared over S plus 2, and we got K equal to 4. And yeah, this is the flow chart. We start with plot the root locus using the MATLAB and find the dominant pole with temperature 0.707 and calculate K using the formula. Next. Next, I pass to next member.
Hello, Doctor. I will present the next for question 2.
Video on. Video on.
Yeah. Question 2. A large antenna as shown in the 7 is used to receive satellite signal and must equally track the satellite as it moves across the sky. The control system uses an armature control motor and a controller to be selected as shown in figure 57.60. The system certification provides a steady state error for rank input RT equals to T less than or equals to very constant. We also seek a percent overshoot step input of less than 5% with a settling time with a 2% criterion of less than 2 seconds. Question 2A. Using root locus method, create an file to assist in designing the controller. Next, for the manual calculation about this problem, first we have to uh, based on the requirement, which is 5% percentage of the suite. We use this equation, and we can find the damping ratio of the required system, which is 0.69. And by using this equation ES equals to 4 over delta omega n, we can find the omega n, which is this. And by using this value, we can then find the dominant closed loop pole, which is -2 plus j 2.098. And after we find the closed loop dominant poles, next for the system, we need to find the one zero poles that will be added into the system. So we use this graph and we calculate the angle of each to find the angle of the required zero poles. Use this formula, and the angle is 3.29 degree, which is located somewhere around here. Okay, and this is the extension of the calculation. This is the distance between the closed loop dominant poles and the added zero pole, and the location of the zero is negative 38.5. And so we also calculated the gain of the new gain, which is 2.38, and then we get this equation, and we plot to the MATLAB using MATLAB. This is the flowchart. Use TS to find omega n, find closed loop dominant poles, find added zero poles, find new gain, return function to plot step response. So this is the uncomposite system. Basically, this is the question, and we can see the percentage overshoot here already below 5%, and then P ratio we find 0.69, and settling time here, and this is our body. Find this graph. So after we have done the calculation and the system with PD controller, we use this MATLAB code and use the new equation to the compensated root locus. And as we can see here, we next is
Okay.
Hi, I'm Ashraf. Okay, for the question 2B, we need to plot. First, we get the uncompensated system step response from the MATLAB, and then this is compensated system with PD controller step response. Okay, this is step response that I plot using Excel, and you can see on the right, and then the calculated version different ratio is 0.69, natural frequency is 0.9, and settling time we got from calculating the using formula 4 over different ratio and natural frequency, we got 2 seconds, and percent overshoot we got 1.942, which is different, a bit different from the MATLAB. See, there's from the MATLAB we got 4.6%. Meanwhile, we from the Excel we got 1.942, which is expected to be a bit different. And this is both plot. We can see the gain margin and phase margin. And for question 2C,
This determines the effect of the disturbance TDS equal to Q over S, which is on the output by S. So the question asks what will happen if we add disturbance to the system. For example, Q equals to 1, and the disturbance will be 1 over S over here, and this is the output, which is we already combined with the disturbance, and we see the result over here. And this is the step response, which is exponentially this is because the is 1 over S, and when we add 1 over S into the system will be the C-side will be increased by 1, and this is the root locus for the system. And so the result of the disturbance is resulting for the system to be unstable, which is exponentially increasing. So we don't want this as the result. Discussion.
Over here we can percent over and then we analyze bit by bit. PD for the okay.
Okay. Hafiz,
Yes, Doctor.
last minute question. Ni, okay. Dalam reality life, dalam kehidupan sebenar, apakah disturbance yang berlaku pada sistem ini? Contoh.
Contoh disturbance.
Siapa-siapa boleh jawab? Aidil boleh jawab, Hafiz boleh jawab, Ashraf boleh jawab. Sistemnya antena. Okay, so apakah disturbance yang benar-benar ni, yang real punya? dalam kehidupan sebenar?
Uh, maybe the disturbance, maybe we can say earthquake
Ha?
on the earthquake on the
Earthquake dah tombang dah benda ni. Tak ada.
Wind. Strong
Ha?
wind.
Wind.
From the wind, strong wind. Push.
Okay, wind gas lah. Wind gas.
Wind gas.
Lagi? Ashraf?
Saya Ashraf.
Ashraf.
Saya Ashraf.
Hafiz?
Hafiz.
Contoh lagi tu?
Adil.
Rain.
Rainwater. Heavy rain.
Ya.
Macam sekarang lah tadi putus kan. Itu kira disturbance lah tu.
Oh, disturbance.
Lagi Aidil?
Maybe tornado.
Lightning strike.
Lightning. Okay. So itu boleh masuk dalam slide lah.
Okay.
Kenapa tak ada Excel?
Yeah, but
Ada?
nanti saya email balik. dah buat, tapi lupa nak masuk sekali email.
Masuk balik dalam slide.
Doktor nak tengok ke?
Mesti dalam slide. Tak boleh di luar.
Okay, data nanti saya letak.
Lepas ni kita orang submit.
Okay. Exit group number 9.
Thank you, Prof.
Okay, thank you, Prof.
Unshare.
Okay.
Group number 9, Chiang Yongji.
Yes, doctor, I'm here.
Share your group member.
Yeah, my group member also here. So let me share my screen. Yeah, Nigel and also Noah. Okay.
Wait.
Okay.
Noah?
Yes, doctor. Sorry, let doctor now.
Go, Noi, Jen.
Okay.
Go mana?
Hi. I'm calling.
Yongji. Jin Yongji.
The one,
Yes.
nine got ready.
Kamu semua sabar, Pak?
Tak, seorang. Me and best seorang.
Noi, mana Noi?
That one. That one. Got 9 present.
Pulau Pinang. Sorry. Lupa ambil.
Yongji.
Oh, saya Sarawak.
Okay. Silakan.
Okay, so let me share my screen.
Ideal. Exit group.
Sure. Okay. So good afternoon, doctor. So our group is consisting of me, Yongjie, Nigel, and Noah. And the question that we are given is actually set 3. So I will be the one who's starting to explain about question 1, and then followed by Noah and also Nigel. All right. So as for my part, right, so I was given the question 1. So in this question, I was given a feedback control system as in the diagram. So there is a controller and also a process equation. And they are given 3 equation, which is K over S, K over 1 plus 1 over S, which is P controller, I controller, and also PI controller. So I will need to design a specification that are less than percentage error of less than 10%, and also the setting time of less than 10 seconds. So for the proportional controller, I will need to develop an N file to sketch the root vectors for the K value from 0 to infinity, and also to determine what is the K that is able to meet the design specification, whereas the percentage error, percentage overshoot is less than 10%. Then I will need to repeat for 3 of the controller, P controller, I controller, and also PI controller. Then I will need to call plot the unit step responses for 3 systems together. And last but not least is to compare and contrast the 3 controller in terms of steady state errors and also the transients performance. So this is how I develop the solution. So I will explain about the flowchart of how I do the manual calculation and also the simulation steps. So first of all, I find the pose for the transfer function, and then I plot it out on the graph paper. I draw the asymptote line, calculate and draw the asymptote line to see whether there is exist of the y-intercept. So if there is, the asymptote line is not 90 degrees, they are proceeding to calculate the JW crossing by using RH table and connect the breakaway point with J omega crossing. So after finding the breakaway point, then I will find the angle given according to the specific percentage overshoot to obtain the dominant pole. And last but not least is to determine the gain from the graph. And this is how I develop the MATLAB simulation. I define the open loop transfer function and also the omega for the P controller first, and to plot out the root vectors. And after plotting out the root vectors, I will use a cursor in the MATLAB to determine the K value and the dominant pole. And next, I will plot the step responses and call plot 3 of the responses together for each controller. And last but not least is to compare and contrast after obtaining the steady state error and also the transients values from the graph. So I will continue on with the first one, which is the P controller. And this is the equation of the P controller that is existing of the poles, and the branches are 2. And after obtaining the asymptote line, I will be able to draw the graph. And next is to find the roots and also the breakaway point. So for this question, since the asymptote line is actually 90 degrees, so there is no intersection as the y-axis. And this is the graph that I managed to plot by using manual calculation. And this is the angle by using the determined percentage overshoot that I determine is actually 8%, and the degree would be 51.2 degree. And by using the calculation,
what is theta? What is theta?
Sorry?
What is theta?
Theta, right? Theta is actually for me to see the degree between 8 degree to reach out the K value point, the intersection of the asymptote line.
Wrong. Noah Jamal, what is theta? Noah Jamal, what is theta?
Theta is the value of damping ratio. When we find the damping ratio, then we can find the theta using the graph.
Wrong. Noi, what is theta?
Theta is where the line intersect with the root locus.
Wrong. Theta.
To find the dominant pole.
Wrong. Theta is the angle of damping ratio line.
Using the
Tembak
kan dokter, tembak the line. Can use
tembak
the formula.
tembak nanti markah rendah bah.
Oh lah.
Teruskan. Continue.
Okay, continue. Okay, so this is a calculation that I have made, and I continue on with the I controller. And this is a calculation that I follow from the flowchart that I did, as well as I just like follow through the steps, calculating the poles, the branches, and then continue on with the RH table in order to plot out the graph and obtain the K value that I had get. And similarly, I also determine 8% as a percentage overshoot because the requirement is less than 10%. And continue on with the PI controller. I also follow up the steps that I set up in the flowchart to come up with the manual calculation, and I managed to get up each of the gain value for P controller, I controller, and PI controller. And after getting all the manual calculation data, then I continue on to proceed with the MATLAB simulation. And this is the MATLAB source code that I do for question A. So what I did is actually I add on the angle that I get from the angle of the angle, and then I plot it out in the graph first, because this one would be help me to actually see and move the cursor more easier to get the K value. And also I also generate the stat responses by using the feedback and also the stat syntax in MATLAB. And similarly with question B and also question C for PI controller and also PI controller. And next is to call plot. For the question D is to call plot 3 of the root vectors and the state responses for 3 controller together in one plot. So how I did it is actually I use hold on and also hold off, so that both of the 3 steps generated from the MATLAB is able to display in one graph. And this is the simulation result for question A, which is the P controller. So based on the chart given and based on a degree of 51.02 degree, and I will be able to get the gain of 10, and the percentage of S is determined as 8.09. So this is similar with the one I showed Dr. just now, which is the gain value is 10. And also I plot out the step resolution to get the settling time, which is 1.5 less. Okay, okay. So next, also similarly, I did the same steps for the I controller to get the K value. So the K value is 4.12. And next one would be the PI controller. So PI controller, the gain that I get is actually 8.66. And this is the result that I call plot 3 of the state resolution into one graph. And after getting all the data that I explained just now, I put it into a table. So this is how we are able to see it clearly. So I can, from the data that I obtain, right? So I can come with a conclusion that actually P controller has the highest peak overshoot and require short time for the system to stabilize. But there is a presence of steady state error as follow the table. However, for I controller and PI controller, there is no steady state error because it is able to eliminate the steady state error. I controller has a slightly lower peak overshoot and a slower response, while PI controller has the lower peak overshoot, the lowest one, which is 0.95, and a faster response. And this is a discussion that I have made. So there is some improvement that we can make from this system. So what I can think about is like 2 ways. One is the Diggers-Nicholas for the parameter tuning, and also the we can try it out with the PD controller and also PID controller. And this is the learning process that I get. So I have performed the stability analysis and controller design based on the MATLAB and also manual calculation. So this is how I also able to learn the MATLAB simulation for this question. So next I will continue, I will pass to my group mate.
Yeah, my turn. Okay, so basically I do for question CP 7.8. So consider the spacecraft single axis attitude control system shown in figure CP 7.8. The controller is known as PD controller. Suppose that we require a ratio of KP over KD equals to 5. Then develop an M file, MATLAB file using root locus method. Find the values of KD over J and KP over J so that the settling time will be less or equal to 4 seconds, and the peak overshoot is equal or less than 10% for unit step input. Use the percent criterion in determining the settling time. Like, okay, so this one is my flowchart for manual calculation. So firstly, I simplify the LTF, the open loop transfer function. Then I find the damping ratio. Then I find KD over J and KP over J using CLTF. Then subs value into KDJ and KP over J into the OLTF. Then I can find the open loop transfer function. Then I can find the zeros and poles. And then I find the real axis break-in point. Then draw the root locus. And then find the angle using the value of Dempsey ratio obtained. Then next, obtain dominant pole from graph using angle calculator, and then find the settling time TS using the dominant pole obtained. And this one is for my MATLAB for root locus. So first I start and then define the open loop transfer function and then plot root locus and then finish. For the step response, start and then define the closed loop transfer function, plot time response, then end. Okay, this is my manual calculation. So firstly, I simplify the OLTF, this, KP over this, and then finally this, where K is equals to KD over J. Okay, and then second, I find the damping ratio from the given overshoot equals to 10. So this is what I mean by I shoot the graph doctor like this. So the value of overshoot is 10, and then I find the value of temperature using the overshoot. Okay. And then from the just now, then I can find the angle of the damping ratio equals to 53. Right. Yeah. Then next, I find the value of KD over J and KP over J using CLTF. So I firstly find the CLTF for the OLTF just now, like this. And then I do a comparison between the CLTF. And then finally, I can get the value of KD over J and KD over J and KP over J. Like that. And then after that, I substitute the value of K, the K over KD over J into my open loop transfer function, this one, so that I can draw the root locus graph. Like this. This is my root locus MATLAB simulation for root locus. Okay, so we can see here my graph. Back. Right. So from here, you can see my zeros is -5 and my poles is 0 and 0. Next. Okay, this one is my root locus. Right. Okay, next. Okay, and then I find the real axis break-in point. I firstly differentiate the open loop transfer function, and then finally I can find the break-in point.
Laju sikit Noah.
Okay. And then this is my MATLAB simulation for break-in point. Here I just move the cursor to find the break-in point. Okay, next. Okay, this is my manual solution for root locus graph. So I basically draw the root locus using manually. So like this.
Mana
So that,
Excel ni bah?
apa?
Excel.
Oh, for the Excel doctor, we haven't do the Excel.
Ada Excel markah rendah bah?
Okay, dokter. So nanti kita orang buat yang Excel.
Contoh hari Sabtu.
Boleh dokter. Okay.
Semua.
Okay.
Jinwei semua. Yongji semua.
Okay, doktor.
Okay, dokter.
Teruskan.
Okay. Can proceed. Dokter can proceed.
Ya.
Okay, thanks. Okay, see, this is the value for the settling time obtained from my manual calculation. So what I get, this is my dominant poles for manual equation. So the settling time is 4 over the real part of the dominant pole. This, so I get this. Next. This is the MATLAB simulation for the dominant poles. So when I do the MATLAB simulation, I find the value of dominant pole, and then it is slightly different from my manual calculation because of the decimal point that I have used. Next. This is the time response graph MATLAB simulation. This is my settling time. Next. This is my MATLAB code for root locus. Yes, firstly I define the open loop transfer function, and then I just root locus system, then create. So I only need to move the mouse to find each value of roots, real axis, breaking point, and dominant poles. This is my MATLAB source code for time response graph. Okay, discussions. So my observation is the value of dominant pole and settling time Ks can be obtained manually from root locus graph, and it is slightly different from the value obtained in simulation because of the decimal point that I've used. Okay, so
Okay.
if I want to,
Okay. I think go to Noi.
okay, thank you, Doctor. All right.
So presenting question CP 7.9. Consider the feedback control system in figure below. Develop an N file to plot the root locus for k greater than 0, less than infinity. Find the value of k resulting in a damping ratio of the closed loop poles equal to 0.707. So next. So this is my flowchart of this assignment. First, I write the MATLAB code to plot the root locus, then draw the root locus using manual calculation and compare the root locus. If they are the same, then proceed to next, which find the dominant poles and value of k using manual calculation, and use the mouse to drop the mouse in the graph of MATLAB to determine the dominant pole and k value. Then compare the values. If same, then success. If no, then repeat the manual calculation to make sure the answer is same. Next. So the manual calculation for plotting the root locus. First, we find the poles or the transfer function, then find the asymptote line. Next, so the poles of the transfer function can be proved by these 3 points in the graph of MATLAB. Next. Then find real axis breakaway point by differentiating the transfer function, assuming k equal 1. Then we obtain a breakaway point, then prove by MATLAB. Next. Next. Then find the j omega crossing using RH table, and we obtain the j omega crossing as is equal to plus minus j 3.87. Next, and proof by the MATLAB. Next. So given the damping ratio is equal to 0.707, so the theta is equal to 45 degrees. From the graph drawn, a line is drawn from the origin at 45 degrees, and the line intersect with the root locus is determined as a dominant pole, which is this value. Then from this, after obtaining this dominant pole, we sub into the transfer function and then find the k value equal to 9.2. Next, this is the root locus draw. True. So this is the next. So in MATLAB, the K gain value is 9.15, which is slightly different from my calculation, 9.2. Next. So this is my MATLAB source code. Looks short but quite fun, but it's functioning. Next. So from discussion, as a result, the type
What is KP?
KP is position error constant.
Okay.
So since the type of the system is 0, so we use KP to calculate the steady state error. So KP can be calculated using this formula where K is equal to 9.2, and we can obtain a steady state error is equal to 0.22. So this steady state error can be improved by using compensators such as PI controller and etc. So by increasing the gain, the steady state error will reduce, but OS will increase. This method will change the open loop poles and zeros, thus creating a new root locus that goes through the desired closed loop pole location. Next. So in this assignment, I have proved my knowledge related to root locus, which I have studied in this course, control system design. So I have successfully drawn and refined the root locus for the transfer function given and proved using MATLAB. The small difference between manual calculation and simulation can be ignored as the decimal place used in manual calculation may be a bit different. Yeah, that's all from me.
Thank you. Okay.
Okay.
Group. Exit group. Okay. Thank you very much.
Thank you, Doctor.
Thank you.
Okay, thank you, Doctor.
Group number 18. Group
Yes,
number
Doctor. Yes.
Andor and Osama. Sama.
Okay.
On
Yeah.
video. On video.
Okay.
Share slide.
السلام عليكم.
كيف حالك؟
الحمد لله.
بخير.
بخير الحمد لله.
بخير الحمد لله بالخير.
بخير.
مستعين؟ Ready?
إن شاء الله. بسم الله.
بسم الله.
Okay. Okay. Okay, this is our presentation. Me and my group member Mamdouh. My name is Usama, and my other group member is Mamdouh. This is the assignment 5 of control subject. Okay, this I I was enrolled to do this question using bootplot to design a phase lead compensator to meet the following specification, which is TS is equal to 2 seconds and percentage of overshoot is 10. Okay, so for the manual calculation, since I'm given the overshoot, I calculated. From the graph, I find the zeta is equal to 0.6. And from graph zeta against the phase margin, I get the margin. The desired gain margin is 59.2, and the settling time should be 2 seconds. Now I find the open loop transfer function. I multiply the the actuator, multiply the aircraft. Then I find the open loop transfer function. Then from the wood plot, I find that the omega phase margin is equal to 3.13. So the phase margin is 4 degree. Therefore, the required phase margin is equal to the 59, the desired minus the actual phase margin plus the correction ratio. So I get it 60.2. Then I calculate the phase margin max to find the beta. I got the beta. Then at phase margin equal to 60.2, we get the omega max is equal to 1.14. Then I start to calculate the the compensator value. I get the from the omega max the dB value of the lead compensator is 3.79, 1 over square root of beta. Then I get the value from equation omega max is equal to ZC over square root of beta. I got the value of ZC. Then I got the value of BC, which equal to 4.31. So now I get,
Sama,
yeah,
slide.
yeah,
Slide is not
yes.
moving. Slide is not moving.
It's moving.
Slide is not moving.
Can see or not?
I see just the front slide.
It's showing
There's the
the
slide.
slide
Oh,
only.
wait, I will stop sharing. Again, screen. Now, doctor, is it clear?
Move slide.
Now is it clear? Is moving or not?
Moving.
Moving, right?
No.
Not moving.
Moving.
Okay, so I will wait. Like this is moving, right?
Okay.
Okay, I will like this. Okay.
Okay.
So should I re-explain?
No need. Lead compensator, go straight away.
Yeah, okay. I got the value of the lead compensator,
What is
which
the
is sorry?
What is the lead compensator? The value?
This one, the lead compensator value. It's no, this is the open loop transfer function with the lead compensator. The lead compensator I got is 14.3, and for the zeros is 0.332 for the ZC, and for BC is 4.31.
Okay.
Okay. Okay. Now this is the body block before the lead compensator. We get this is the value of the phase margin at 3.313. It's equal to the 4 degree, and then this is the lead the system after the lead compensator, and this is the Nyquist diagram, which we get the big gain is equal to 48.2. And this is the ball zeros map of the closed loop transfer function, and this is the MATLAB code we use. And this is the the root locus of the system, and from it we get the settling time, which is 4 over the real part of the system, which is 2.2, and which is almost similar to the requirement. So that's all from me. I pass to Mamdouh.
Okay. For my question, it asks to get a lag compensator using the root locus method to meet the following criteria: a phase margin of a greater than 45 degrees and TS of less than 5 seconds with a steady state error less than 10%. Next slide. For my solving here, I got a little confused at first, but first I tried to get our zeta using the equation of 45 equal 10 for -1. 45 is our phase margin. 10 -1 2 zeta over root -2 zeta plus 4 plus 1 plus 4 zeta squared, which we got the zeta equal to 0.42. Then I brought our WN, which natural frequency, using the equation. After that, I went to bring our dB, negative zeta plus WN plus J, JWN. So we have here the real part and the imaginary part for our dB. After finding our dB, we needed to bring the KB using the steady state error given of less than 10%. And then you can see what. Yes, thank you, sir.
Okay, never mind. Okay, proceed.
Proceed. Okay, then I plotted. We have the step response plot. The red one is after the adjusting of our sorry. The red
System.
one is after the adjustment, and the blue one is before the adjustment of the lag compensator.
Excel, using Excel.
No, this is MATLAB, but online. MATLAB online.
MATLAB online.
Yeah.
You don't have any Excel, Osama? Excel and
Yes,
Simulink. You should
using
include,
Excel.
you should include Excel and Simulink in your attachment in your report, because I don't see any Simulink. I don't see any Excel.
Oh, Simulink and Excel.
Must have PowerPoint. You must have M file. You must have Simulink of your face lead and face lag, and then your Excel.
Okay. Will include.
Otherwise, if you want to see like this, the marks is quite low.
Okay. We will we will do the Excel and the Simulink.
Saturday is the last day. Saturday.
Okay.
Okay. So today we should submit before 12 p.m.
No need lah. Saturday, take your time.
Saturday. Okay. Inshallah. Okay.
Okay, continue.
Continue.
Yeah. Naam.
Here we got the
quiz,
diagram.
No need. This one. Delete.
No need. Okay. Go down.
Delete. This one, okay. Next.
This the point 0. Next.
Okay.
And this is our loot locus before doing our adjustments.
Okay.
Next.
After.
Yeah, and this is our loot locus after adjustments. As you can see, it's gone. Yeah, it's had been shifted, but not too much.
And then thank you.
Yeah, thank you.
Okay, no reference. Minus marks. No references.
Oh, reference. I forgot to put
conclusion,
references.
minus
Right.
mark. No conclusion, minus mark. No discussion, minus mark. No Excel, minus mark. No Simulink, minus mark. So at the moment, your assignment marks is 4 over 15.
At now 4 over 15.
Because no Simulink file, no Excel file, not detailed. So,
Okay. So we will include the conclusion and the Simulink file and the discussion.
And discussion for each.
Okay.
One
Okay, doctor. Inshallah, before Saturday we will settle this.
Last question. What is the difference between phase lag and phase lead? 3. Reference. Number 1. Wahid. Mamdo. The difference between lag and lead. Mamdo, what is the difference between lag and lead compensator?
The difference.
Number 1.
Well, the lead compensator shifts our plot.
Osama Mamun, what is the difference between lag and lead compensator?
The difference, I think, is for the ZC and the BC. For the lead compensator, the ZC is smaller than BC, and and for the lagged compensator is the BC is larger. It's smaller.
Okay.
I think.
That is number one. Wahid. Number two is 9. Mamdo.
Number 2,
Function.
the difference between different. I think let compensator.
Lead compensator is
lead
improve transient
compensator.
response. Lag compensator to improve steady state error. Number 2. Hello.
Yeah, yes, doctor.
Mamdo.
Yeah.
Lead compensator to improve transient response. Lag compensator to improve steady state error. Number 2. Number 3, Osama Mahmud.
Number 3, I'm not sure, but
That one you should include in the conclusion. Beta. Beta is the ratio of ZC over PC.
of the silver BC. Okay.
For lead compensator, beta is less than 1. For lag compensator, beta is bigger than 1.
Bigger than 1.
Halas. Huh?
Okay.
Okay, Mamdo.
Okay.
So your report is very, very brief, like a school children. Last minute work and not satisfied. So the marks now is 4 over 15. If you satisfied, if not, you submit again on Saturday.
Okay, inshallah. On Saturday we'll submit, doctor.
Detailed and complete with 4 attachments. PowerPoint, Wahid,
okay.
9 M files. Number 3, Simulink file.
You mean the files of the MATLAB?
Yes, Simulink file. Number 3,
okay.
Number 4, Excel file.
Okay, inshallah.
Excel to compare with your
you mean, doctor, you mean that from the Excel we should get the graph from the Excel, then send you the Excel.
Yeah, the graph must be same like the one you show in the MATLAB. The rule locus, the time response.
We should do it in the Excel.
Yeah, do both MATLAB and Excel.
Okay, inshallah. MATLAB and Excel and discussion, the reference, inshallah.
Like number 4 is okay, but if you want good marks, so you have to include all the attachment.
No, okay, doctor. Inshallah, we will include all.
Subhanallahi wa bihamdihi, subhanallahi wa bihamdika. والعصر الإنسان لفي خسر إلا الذين آمنوا وعملوا
الصالحات تواصوا بالحق وتواصوا بالصبر.
السلام عليكم ورحمة الله وبركاته. إلى اللقاء.
وعليكم السلام دكتور. Thank you.
شكرا حبيبي.